Hi, welcome to Don's Manufactory. You know, I've been thinking about something, and I think it's time to document this, and that is, I think points get a bad rap. Betsy's been running on points since she was born. First with the 6-cylinder, then with the V8. Still running points. Never had a lick of trouble with it. I know people say they're too much hassle, they take too much adjusting, you gotta fiddle with them all the time, they're not reliable. I beg to differ. You know, before electronic ignition, points ran the world. Everything that had motive power used points. Yeah, even your electric motor used relays, points. Even in your modern car, you have points running. There's relays in your car running all the stuff. Points have been relied on for decades and decades. It just got me to thinking, what the heck is wrong with me? It got me to thinking just how to go about explaining what happened, what went wrong, and how we ended up where we are. Now, this is going to be talking Ford, because this is going to be the history of points ignition on Betsy and Fords in general. Back in the 70s, I had a tune-up shop, so I saw a lot of Fords, and I was buying a ton of parts, and things just went awry. Just to get started, we'll just talk about what the problems are and what solutions I had at the tune-up shop and whatnot. What happened history-wise. And then we'll get into an analysis of the physics and all of that, which, I don't know, some of you may get, shall we say, tune out when I start on the math part of it, the physics and everything. But I think it's a good thing to know. So I think I'll just have you look over my shoulder here, and I'll just sort of explain the history of what happened back in the 70s and early 80s. So before I get started here on explaining what's going on and everything, the first thing, if you guys have been watching my channel for very long, you know that I will have to quantify everything I'm talking about. Otherwise, I mean, what the heck? It doesn't mean anything. This distributor I took apart yesterday because I was looking to see, out of all these distributors I have here, which one is the best to build for Betsy. I may end up just using the one that's in it, but I don't know for sure, because my first problem was finding a distributor that is good. So I took them all apart and started measuring a few things, and you would end up having to do this as well. You can see by looking at this shaft right here that it's got enough of wear on the shaft that I can feel it with my fingernails. Let's see how much wear we got. Let's make sure our thing is, zeroed up just fine. And we'll take it out here, I don't know, 1/2 inch. What size are these shafts? Well, let's just... Okay, 4.467 and a half. Is that about what you'd read that as? Yeah, 467 and a half. All right. And then up here, where we've got wear. Oops. Come on, Don. You can do it. Okay, 466. So about 1/1000 and a half of wear. So what does that mean? Well, There's subsequent wear on that bushing as well, but the bushing can always be replaced. But the deal is that you can hear the play up here on this bushing. So if there's play in that bushing, that means this points cam can bounce around and cause the points not to have an equal dwell all the way around. You know, it's got to be better than that. So now there's this one. This is a C5AF, and it's a 4MA. The tag on it says 289 two-barrel, automatic trans, 65 and 6 Mustang Falcon Fairlane. I don't know what's that. I don't know what that says at the bottom. 1964, December 1st is the production date. Okay, so this one, let's wipe this shaft off. There. Okay, so we'll check this one. This one's got hardly anywhere. I mean, I can feel that, just barely. So let's see, for the main shaft size, we're back to 0.4675. So exactly the same size as the other shaft. Pretty consistent, I would say. It's still 4675. I mean, if there's a tenth of a thousandth of wear, I'd be surprised. So this shaft is in really great shape. And the bushings are in really great shape, and you can tell there's I can't get any clicky clanky noises. So this is going to be a really good core to build. Now you should note that on the bottom here, this bushing is always loose. Right there, you can see the play in it. So that bottom bushing is always loose, and the reason is this is where the bottom of the shaft is stabilized. This surface right here as it runs inside the block. Alrighty, let's see, what else can we measure? One of the things that I want to get to the bottom of, and I just want to, let me do a quick description of it. Let's see if this works out. Okay, we have a distributor. Let me just kind of draw. Okay, 1, 2, 3, 4. Okay, that's a really horrible drawing. Right? So the rotor sits inside of here. So what kind of time constants are we looking at? Generally, I want to spin my car to 6,000 RPM. Okay, so the distributor runs half that, as does the camshaft. It's running, actually, 3,000 RPM. So if we take the 3,000, and that's revolutions per minute, and we need to know, let's get this down to seconds, so we'll divide it by 60. Okay, so 3,000 divided by 60. So that'll give me revolutions per second, which is 50 RPS. How long does it take at a 6,000 RPM crankshaft speed does it take for this distributor to make one? Okay, I gotta turn this dang thing. Somebody just keeps dinging me over and over again. How long does it take to make one complete revolution? Well, that's 1 second divided by those 50 revolutions. Okay? So 1 divided by 50 gives us 0.02, or essentially 20 milliseconds to make one complete revolution. Okay, there's 8 cylinders. Now let's divide this by 8. So we've got 0.020. See? divided by 8, and you have 2.5 milliseconds. 2.5 milliseconds for the rotor to move from this lug to that lug. The points have to close, the coil has to charge, the points have to open, and the coil has to discharge. And all of that has to happen inside of 2.5 milliseconds in order to have the car run at 6,000 RPM. Let's just say we're going to be talking about distributor RPM. Okay, so we're not talking about crankshaft RPM anymore. This is distributor RPM. And we'll talk when we talk about degrees of advance and whatnot, it's all going to be in distributor degrees, which is of course half what you would read on the crankshaft with a timing light. Okay, first off, I ran my motor on the scope. So the scope pattern, there's a rise to the voltage and then a real quick drop to the voltage, and it comes down to a spot, and then there is a line like so, then there's a little peak like so, and then there are oscillations, and those are caused by the condenser coil oscillations. So when the points are open, there's a current wave which is just bouncing back and forth between coil condenser, coil condenser, coil condenser. And the whole point of that is that the condenser is absorbing the energy and helping it dissipate so that the points don't arc. The idea is to get those points to separate when it fires. You want the points to separate and not cause arcing, which will burn the points. All right? Essentially, the voltage will drop down, and this will actually trail down. And then the points will close again, and when it does, it comes down to 0. There's coil condenser oscillations again, and there's a curve up like so that continues until the points open again. So basically this little spot right here, that's the fire line. That can tell you a lot about what's going on in the ignition. If this fire line is elevated up here, then there's resistance in the system somewhere. If it slopes, there's two things that cause the slope. If it's lean, then you get the resistance going up. If it's rich, it goes down. How long this line is dependent on resistance, and it's dependent on how much energy is in the coil. So all of this is going to be about Betsy, and Betsy has a 40, I think it's 42,000 volt a cell coil. The stock one was about 20,000 volts OEM. How long is this discharge time during the fire line? Now there's this idea that all you need is the initial spark, and that's all you need. Well, that's true for some motors, like Hemis. But it's not true for wedge motors that have quench. Now, what this line here is, the point's open, the field is collapsing, and the voltage is going to keep going up until it reaches a point where spark can be established across this gap right here, the gap at the plug, the resistance in the coil wire, the resistance in the plug wire, the resistance inside the plug. Once it overcomes all of that, it will establish an arc, and then the voltage drops rapidly, because after the arc is established, there's a resistance, there's a voltage that the arc will be maintained while there's sufficient current in the coil to maintain the spark. How far is this rotor going to rotate during the fire? That's what I need to know. Because we only have 2.5 milliseconds from this point here to that point here, and we have to be ready to fire again. So running my car on the scope, the discharge time on my coil, and this is real easy to measure. I just ran the motor at 1,000 RPM, and my scope is marked in degrees, and I could just see how many degrees of distributor rotation during spark. What I had was 1 millisecond of discharge time. Charge time, which is from this point here to this point here, was 1.5 milliseconds. And that made up my 2.5 milliseconds. That's what I had calculated out. At 1 millisecond, I mean, if we're going to run the numbers here, we have 45 degrees divided by 2.5 milliseconds. And we end up with 18 degrees per millisecond. 18 degrees of discharge, 27 degrees of charge. Well, that sounds familiar, doesn't it? What's the dwell setting for a Ford distributor with single points? It's 27 degrees. So the factory already knew and was designing for the theoretical limits that this distributor is going to run at. This all sounds fine. Let's find out. Here's a rotor. This is just an OEM rotor. Now we need to find out let me turn the page here. Now I need to find out how many degrees does the rotor represent. So in other words, when it's arcing and swinging past the lug, how far can it swing before it starts moving away from the lug? Okay? So to figure that out, we have let's just draw our little distributor again. It's like starting over. Okay. We need to know what the circumference of the cap is. And that should be easy to measure. You'll notice this cap here, I cut away so that I could see and put this on Betsy and check what the registration is. In other words, I'll be able to just shine the timing light in there, and I'll be able to see where the rotor is pointing when it fires. What I need to do is just measure this diameter here. Now I can do that very easily by just running this over like so and poking her there. Okay, so poke it right there and bring that right up to there. And what have we got? 2.886. Okay, let's see how this works out. 2.886 times pi, 3.14159. 9 inches. Okay, so now we know the circumference of the circle that the rotor makes is 9 inches. Okay, so let's just take that 9 divided by 360. Every degree is 25 thousandths. Okay, 1 degree equals 0.025 thousandths. Okay, so now all I got to do is measure any one of these. Like this rotor right here, we measure that, 350 thousandths. Okay, so down here we have rotor equals 0.350, and we divide that. So we divide 0.350 by 0.025. 14 degrees. So the rotor can only swing 14 degrees. I hope you're seeing a problem already, but we'll see. But we also have a width on the lug plus the width of the rotor, because the rotor does this. You know, it can start over here and be arcing and go all the way over to there. The amount of degrees of swing while we're still within range of the rotor and the lug is the distance of both of those. And fortunately, with this thing cut away, I can just do this, 190 thousandths. 0.190 divided by 0.025, 7.6 degrees. So the lug equals 0.190, which equals 7.6 degrees. You add those together, 21.6 degrees is what we can cover using stock components. 21.6 degrees. So, what situation do we actually have in the distributor? Well, the first thing is mechanical advance changes. Let me just pull the shaft out. The mechanical advance changes the relationship between the distributor and the engine. So it's turning the bottom part of the shaft. So when it advances, the rotor remains in the same position because of the way the mechanical is changing this relationship. It's not changing the relationship between where the rotor is pointing and where the points are firing. Okay? Betsy also has vacuum advance. Okay, remember, we're talking all distributor degrees here. The vacuum advance is 11 distributor degrees. What we have to cover here is the discharge time, which equals 18 degrees. I have to cover 29 degrees of rotation at 6,000 RPM with the rotor cap interface. But that isn't going to happen because we can only cover 21.6. So what's going to happen here? Well, one of the things that you notice on fire lines is they can slope up. And especially when you start revving the motor up, they'll slope way up. They'll slope up from the mixture being lean and increasing the resistance, but also they will slope up when the rotor starts swinging away from the pole piece, from the lug, by 7.4 degrees. That's like another 190 thousandths. So how can I fix this? Well, I could take the cap, or the rotor here, and silver solder, a little piece of copper on there, some thick copper, and extend the tail of this. And we need another, 7.4, 7.6, we need another 190 thousandths or so. So let's just make it 200 thousandths to be safe. We have 350, so that would mean 550. So let me go out here to 550, right about there. Come on, Dawn, you can do it right there. Okay. So in order to have a good solid run and discharge the coil completely, the rotor needs a tail on it like so. You can do that, or you can do what I did. Let me grab my parts bin here. So here we are. Here's one I was just playing with. And I just made a new brass lug for it. I pulled this pin out, machined a new one, stuck it all together. And this one measures bigger than it needs to be because I haven't finished machining it. But it's 560 thousandths, so it's 10 thousandths bigger than it needs to be. This is the fix for that. So let me show you how this all works out inside the distributor. And I'll show you some of the problems I've been having with Betsy. Now this is just, I'm going to say it's pathetic. Okay, let's put the rotor in here. And we're going to put this specialty Deschel cap on here. Okay, there it is. So, another thing that I did was, let me just stick this in here. It's a little something I just whipped together. It's a little LED strip, bing, so I can light the inside of this here. There. The arc can start there, and it can run here. So the problem is that when you have a vacuum advance moves the distributor plate, which is changing the relationship of where the rotor and the points are firing in relationship to the lugs on the cap. So unlike mechanical or centrifugal advance, vacuum advance changes the registration. So you have to have it aimed pretty close to center, maybe a little early like so that you can cover 11 degrees of vacuum advance. So when you're cruising along at, say, 2,000 RPM and the vacuum advance is pulled all the way on and you're on the freeway, this is where the rotor is firing inside the cap. Right on the edge there. Now, you stab the throttle, and as soon as you do that, it snaps back to here, and then the mechanical advance, the centrifugal advance, opens up with RPM, and it's not changing its registration, but the discharge time on the fire line is 18 degrees, which then puts the rotor over here. So as the RPM goes up, what's cutting off the spark isn't that the coil is running out of energy, it's that the rotor is pulling away from the lug. So then you have excessive, as you go up in RPM, you'll start having excessive energy left over in the coil, which causes this secondary peak to go way up, which makes these oscillations go really big, and then arcs the points more. If you look at all of these numbers and everything, we have 18 degrees of discharge time, which is 36 crankshaft, right? Isn't that just about what your total timing is? 36 degrees? You want spark happening in the combustion chamber during the entire quench period and a little bit after top dead center. What that does is the turbulence in the cylinder from the quench keeps blowing unburnt fuel and oxygen past the gap in the plug, and the plug continues to fire to ignite it. So you're not relying on the flame front traveling. The quench and all the turbulence and swirl that it causes, that and the spark continuing during that period of time, that's where efficiency and power is maintained, or made, I should say. Having that extra length on the cap or on the rotor is going to ensure that I get a quench spark happening during quench all the way up through 6,000 RPM. But as you can see, it's kind of a theoretical limit. I mean, how would I go faster than this? And the answer is, I wouldn't. If you look at the way this thing is structured, let's say we have the coil right here, okay? So out of the coil is a resistor wire. This is the coil wire, and it goes to the cap, and the cap has an air gap. So you have resistance there because of the air gap, and then you're going through a resistor wire, which is connected to a resistor plug, which then has to spark another air gap to go to ground. So all of this resistance is what makes the fire line as long as it is. So you have to ask yourself, how did Shelby do it? You know, he held up that sign, 7,000 plus, go like hell. Well, how in the heck are they going to go 7,000 RPM when you're not going to be able to maintain contact with the rotor and the cap? Well, the first thing they did was no vacuum advance. So that means we don't have to, if we go back to my little formula, you don't have to cover the 11 degrees. You only have to cover, it's actually more than 18 now, because you're going to be doing 7,000 RPM. You know, that's another, what, 15% longer? You can cover 21 degrees, so you can go higher with the stock setup. But the other thing you're going to have to do is you can't shortchange the charge time, the 1.5 milliseconds of charge time. So what did they do there? They went to dual points. So now you're running 31 degrees of dwell. But the other thing you're going to have to do is you have to reduce the resistance. And so for Shelby, in order to run those kinds of RPMs, we had solid core wire, we have solid core wire, and we have non-resistor plugs, and then the gap to ground. So basically the only resistance in the circuit are the two air gaps. So with less resistance, you'll have a shorter discharge time, and then with a dual point you have an extended dwell time. You have more dwell, or you've extended the time for charging the coil. So now the coil still has enough time to charge, and it's still going to discharge all the way, and you'll still have fire all the way through quench. You can put a resistor anywhere in here, like, it's cutting off before top dead center. You know, the discharge time is still too short this way. Well, you can put a resistor coil wire in it, or resistor plugs, and leave the rest solid core wires. So you're adding just a little resistance, and that would extend the fire time. So you can adjust the fire time so that you, at your maximum RPM, you still have fire through the quench. Okay? Does that make sense? You can even, another thing that would change charge time is at the head of the coil, there is a ballast resistor. Now, the one in Betsy measures about 1.2 ohms. So what if you just went in there and cut 25% of the length of that out so that it was, say, 0.8 ohms? Okay, now the coil is going to charge faster. So it doesn't need as much dwell time in the distributor. Of course, you're adding more current to the points, which is going to wear them out sooner. But in a dual point, they split the current across the two. One set of points does the opening, the other set does the closing. So each set of points has half the wear that they would normally have. So the system survives. So you see, it's a balance of all these things that allowed them to go to 7,000 RPM. So then ask yourself, MSD distributors that use a stock diameter like this, are they going to suffer from all of the same laws of physics? The answer is yeah. Especially if they don't have mechanical timing or a centrifugal advance unit. If you are controlling the timing via electronic means, now every degree of advance that you put on this thing is movement of the rotor, because you're changing where it's firing like this. You know, you're not changing the relationship between the distributor and the engine. It's all done up here. So now you have the same problem, only worse, because you have to account for, I'd say 26 degrees of centrifugal timing plus the 18 degrees of discharge. So it's even worse. So if it's a small diameter distributor, you're going to have to run, it's going to have a mechanical or centrifugal advance that you have to curve. That's the only way you can get all of this to happen within the allotted, 2.5 milliseconds for 6,000 RPM. 7,500 RPM is going to be 2 milliseconds between lugs. So you get that? That's the physics that's going on and the problems. So let's talk about what happened and how. So we'll get rid of the numbers for a minute. You can rest your brain. This is an OEM distributor plate. So problems that go wrong with these, this bushing here wears out, and this one here is in actually really good shape. The other thing that goes wrong is this pin right here where the vacuum advance pulls on it. And if you look at this, you can see how much play there is. There's just a ton. Okay, so that's going to cause your points to jump all over the place. So that's just basically hundreds of thousands of miles there and no lubrication. Things were left to get rusty. So what happened back in the 70s was electronic ignition. When that came along, the OEMs stopped producing their ignition parts, the standard ignition parts. The first thing that happened was aftermarket companies started producing vacuum advances. Now, the problem with these vacuum advances is that there was no standard for the distance between mounting, this mounting point here, and where this hole is out here. These could be shorter, they could be longer. So what was happening was you'd replace the vacuum advance, and let's say it pushes the plate over like this. Well, we've got two different arcs here. There's the arc of the rubbing block, not the rubbing block, but the cam lobes. And then there's the longer arc from this pivot point off to the side. And you can see how they don't follow each other. This top plate does not move concentric to the center of the shaft. So what that means is, if it's over like this, and then the vacuum advance pulls on, it's going to open up the points and the dwell's going to go way down. If it's starting over here, so it's past center, then when the vacuum advance pulls on, the points are going to close and the dwell goes real high. So without a stable dwell, you're not having the proper charge times, discharge times, and your points burn and the motor runs bad. So for a while, I was bending these arms. In fact, I have a sample in here. Let's see if I can find it. Here it is right here. You can see how it's got an extra hole in it, and I was bending the arm and trying to make to get the points to line up right. The rubbing block of the points needs to be directly across the cam lobes, the distributor lobes. After a while, what I ended up doing was I would just elongate these holes. So whichever vacuum advance I put on, if it was over like this, then I would just rotate the plate until it was in the right position. See what I mean? And if it was this way, then I would rotate the plate that way. And then it didn't matter which vacuum advance went in. I could compensate for the misalignment of where the points are and get rid of the dwell change. When it's set up right, it's just barely past perfectly lined up. So when you pull the vacuum advance on, it starts off at 27 degrees, goes down to 25 when it's right on the apex, and then goes back up to 27 when it goes over the other side. So you get 2 degrees of dwell change. And the ignition systems were really stable. And I still recommend doing that if you're running a stock system and you want it to run well. So what did the aftermarkets come up with to solve the problem of vacuum advances being weird? Well, they made this plate. This plate here, I want you to see just how loose this plate is. Do you think your points are going to run stable when it looks like this? Now the idea was that it has a pivot point here and a pivot point here being governed by this slot. So the idea was that the points are traveling more on an arc, closer to the same arc as the lobes. So you get less dwell change. And that sort of helped cure the problem of having so much dwell change that the car ran bad. The problem was that these distributor plates are just awful. Let's see, what else happened when all of this took place? Well, here's a whole bunch of points. These are all used points that I have salvaged over the years. I just kept them for whatever purpose. The problem with these are they have weak springs. So if the springs aren't strong enough, then the points bounce. So these aftermarkets are all over the map. Like here's a couple of aftermarket points, and I will just push them against each other here. As soon as I get my fingers to work. Okay. And you'll see that one set of points opens and the other one doesn't. So these points have a weak spring, which means 4,500 RPM, these points are going to start bouncing, and you're done with revving your motor up any higher than that. And if you're running an automatic, a stock C4 or stock C6, they shift at 4,500, so this wouldn't be a problem, would it? But it's a minimalist approach. This one here would go a little higher, maybe 5,000, maybe 5,200, who knows? But it begs the question: how did Shelby? How did he get it working? Well, in the old days, this is what we did. You'll notice this one has 2 springs. So back in the day, they were just tanged over the top here, and you could just double them up. So you'd take 2 sets of points and put 2 springs on one set, and then you had a lot of spring pressure. These would be good for 7,500 RPM, no problem. The only problem is with that much pressure, this rubbing block wears quickly. So, gosh, what do you do about that? Well, a cell, here's some Echlin points. These are the ones I recommend you get. They have 30 ounces of pressure. That's still more than any of the aftermarket points. These are good for 6,000 minimum, maybe a little more than 6,000 before they start to bounce. They only cost $20, and when you go to a cell, you're paying $50 and you're getting the same points. So here you go, CS7550. That's the Napa Echlin part number. All right. So that's my recommendation. If you want to run points that are really stable, these are the ones. Let's see, what other problems were we having? Oh yeah, these things. I got to show you this. Let me turn this light back on. Now look at this rotor, and look how close it is. Let me get it right up there. Look at how close it is to that cap. See that? 30 thousandths, same as the plug gap. All right. So, I mean, that's how it's supposed to be, right? Okay, we're gonna take this off now. Let me turn this light off so I don't blind you. Okay. So, the other thing is, here's a brand spanking new blue streak. Okay, now let's put the cap back on. Now spin this around. Look how far away the rotor is from the cap. Just over 200 thousandths. So, if you look at this thing right here, you know, this gap in here is going from 30 thousandths to 200 thousandths. You suppose that's going to change the resistance and how the motor runs? So imagine what would happen if you go and you buy new tune-up parts, you put a brand new one of these plates in there, and it's doing that, and you've got some flimsy points that are bouncing at 4,500, and this thing makes it bounce at all RPMs, and then you've got a bad rotor that is got too much gap to the cap, and you expect your car to run good, and guess what? It doesn't. In fact, this problem right here, you can put this plate in if it's loose like this. Some of them are a little tighter when they're new, but they don't last very long, and then they're loose like this. It creates a tip-in stumble, and you would swear that it's a carburetor problem, but really you created it when you put this plate in. Some aftermarket companies like Sorensen decided, well, that wasn't good enough, so they have the same exact plate. Back in the 70s, Napa or Echlin had a distributor plate they produced that had concentric movement down the center of the shaft. I used those exclusively for a while, but of course they stopped producing them. especially if it's pushed all the way. But it doesn't take very long to wear, and you can see it's still not stable, even when this is brand spanking new, and it's got that much play in it. Yeah. My recommendation, find a good OEM plate like this, refurbish it if you have to, replace this pin or replace this bushing, and then slot these holes so that you can dial in your dwell, and it'll run better than any of these new plates. Okay, another thing to consider, condensers. Every one of these condensers has a different value. Let's check a few here, just for grins. Let's see if it can make a liar out of me. No, capacitance. I need to. So let's see what this one is. This one here reads 233 nanofarads, or 0.233 microfarads. Okay. Now, this one. .236. And this one. .226. So you can see the problem there. They're all over the place. And now you're going to ask me, how in the heck do you tell which one I'm supposed to use? If everything I buy, it's just random whether it's going to be right or not. Well, here's the deal. When you look at this system right here, you've got the, let's put this one in right here. So you've got your plus voltage here, whatever that is. And you have this resistance here. And then you have the negative side, which comes down to the points. So you have a resistance or reactance inside the coil, and then you've got the points right here, and they have their own sort of inherent resistance. The condenser, with different values, what happens is you have your points. So here's one point, and then you have the other point contact. This one's on the arm, okay? Now, with one condenser, you'll get a peak here and a pit there. Pitting of the points. You've heard about that, and you've seen it if you've changed them. And then with a different condenser, you get the opposite. You get a peak here and a pit there. But if you get the right condenser with the right value, they don't pit and they don't peak. They just stay flat to each other and make contact. And if you look at these points, you can see on some of these, they have wear, like this one here, very little. I don't know if you can see that or not. Let me light that up just a little better. You can see that it's got just a little bit of peaking and a little bit of pitting, but not much. And these points here have maybe 20,000 miles on them. But they're not pitted. So even though they're wearing, they still make and break evenly. When you have a pit and a peak, then the contact isn't cleanly made and broken. And it can start messing with the way the motor runs. But if you get the right condenser in there so that you're not peaking and pitting, then your points will last a lot longer. They'll run a lot longer. Okay? You're going to replace your points and condenser when you do a tune-up. And then your points pit, so they fail a little early, and you buy another set of points and condenser and you put them in. But eventually, what will happen is, if you don't want to do it and just document what the condensers are and try different ones at different values to see if they're pitting, to eliminate the problem, eventually you'll end up with a condenser that is the perfect value for your system's overall resistance and the amount of current that is bouncing between the coil and the condenser and keeping the points from arcing. Well, they're going to arc a little bit, but they don't have any metal transfer. And once you get that condenser in there, don't ever change it. The condenser in Betsy has been in there since 1987. I've replaced points, but I've never replaced the condenser after I got the one in there that prevented pitting. So, now I'm expecting that not to work anymore with Betsy because I'm changing the way she works. I'll have to go into a whole explanation of that, but not here now. I was just hoping that maybe now you guys have a picture of what the problems are with the standard ignition system and how easy it is to make it absolutely rock solid. There is no reason why you should have to do anything with your points, except for like 20,000 mile intervals or even 10,000 mile intervals. Pretty much for you guys running cars and coffee cars, that'll be more miles than you put on the car in the rest of your life. Can run on the same set of points, set up the same way, and just start and run every single day. Takes a little bit of tweaking, just like any system does, but it's not a system that's really bad, and you can take care of all the problems that are created. Do you suppose that cap and rotor clearance problems is a problem with electronic ignition? With the parts quality they have nowadays? Is anybody even checking? You have the same problem with parts quality that killed standard ignition. Anyway, I hope that clears that up, why things are done the way they are, and it's not that big of a deal to make the modifications. For Betsy, I want to run a vacuum advance. The vacuum advance is where the drivability and economy comes from. That's why Betsy gets 22 miles to the gallon or so, or used to anyway, with the T5 and the 3.0 gears. I don't know. I haven't even checked it yet. I don't know what it's getting with the 350s and the TKX. Probably less. But, even if it's 20 miles to the gallon, that's still pretty good considering the amount of power and everything that it's doing. Okay? I hope these numbers do you some good. Oh, yeah. And here is a picture of a Chinese distributor. Now, this picture was ripped off from, I just screenshotted it right off of Auto Restomod. It's a brand new Chinese distributor, and look at it. You can see that this distributor plate is designed for concentric movement around the shaft. No dwell change. And if you're running a Petronix, the idea that you would put Petronix on a plate like this, that's changing the distance between the reluctor and the pickup coil, I just see that as inherently flawed. You would want to correct that problem. Even for the electronic ignition, you can't have the plate swinging like this. And even these plates, even though they're supposed to be okay. Even if you had a Petronics on a plate like this that's dancing like this, the clearance is moving in and out on the reluctor, and the pickup coil is moving back and forth and dancing around. You don't think that's going to cause problems? Oh, yeah. In fact, it might even cause failures. All right, I hope that helps you understand what happened, what the history of points in the 70s, and why a point system is still a completely valid way of doing stuff. Just because it's old, it don't make it bad. What makes it bad is bad parts and bad execution, no understanding of how they actually work. So I hope this helps you out. If you're trying to keep your concourse car running good, you're going to have to avoid these plates and try to find, using a concourse correct early plate will actually make your car run better. So that'll wrap it up. Thanks for watching Don's Manufactory. I'll catch you later.